So I guess we are ready for today's class. How many of you are here? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, around 17. So yesterday I told you about uniqueness and existence theorem, and before that I posed to you some questions, and I had given you 3 examples, and some of you were asking me about this example, which is there in the slide also. Okay, so I told you that your y equal to 1, so this is a constant solution, this is going to be the only solution. So did anybody try, to figure that out? Yes? Okay, so I told you that, just by looking at the right hand side of the given equation, which tells you that the function has to be monotonically increasing throughout, it is going to give you some idea. And apart from that, what you can do, you can try to exactly solve this differential equation. Did anybody try that? In fact, yesterday I heard somebody telling me that 1 plus e to the power x is a solution. And then he or she then withdrew that statement. So did anybody try the analytical solution? Yes?
Yes, sir.
So, what analytical solution it came out to be? So, if you, it was it something like y equal to 1 plus c e to the power x?
Yes, sir.
Okay, so I can guarantee you that, when y is greater than 1, you are going to get a solution like this. And when y is less than 1, or maybe I can put greater than equal to 1, y is strictly less than 1, you are going to get this solution. Then, if you plug in the given initial condition, then you will see that only c equal to 0 is going to satisfy these 2 solutions. Is it okay? Am I correct? Fine?
Yes, sir.
Yeah?
Yes, sir.
So basically, you are going to get y equal to 1 as the only solution. Fine? And I just couldn't interpret, like say, even from the that monotonically increasing part also, you can find something. But I was trying to figure it out, but somehow I forgot it. That is much more straightforward. Even you don't have to walk it out like that. Okay. But anyway, this is kind of a straightforward proof that it is going to possess only one solution. So that is why the solution is unique. And now let me come over to another concept called integral curves, because this, in partial differential equations also, and in some other books, you are going to come across this concept a lot. And this is pretty straightforward. So this is basically what, say suppose I am considering an initial value problem given by this, say 1, and of course I am seeking a solution in the neighborhood of the point x0, or to be precise, if I am considering the solution in a rectangle R, or say that R, again remember that rectangle R can be closed as well as open. And in some book, they are going to tell you about an open rectangle. But eventually, what they are going to do, they are going to consider a sub-rectangle in that open rectangle. Okay, fine. So basically, we are seeking a solution in the neighborhood of x0, y0. Okay. So now, as I have told you, that if I try to find out the solution of this as a family of curve, and then I am going to get something like phi of xy c equal to 0 as my solution. Okay, and then if you plug in different values of c, you are going to get different solution curves. So basically, each of those solution curve corresponding to a particular value of c, it is called an integral curve. That's it. So the meaning of integral curve is nothing but it is a particular solution. That's it. Okay, it is a particular solution, and the graph of that particular solution which satisfies this differential equation, and of course that graph, that curve, it has to pass through the point x naught y naught. So this is called an integral curve, and there are ways how. Again, I have already told you about your direction field. Direction field probably in my first or second class, I exactly don't remember. But anyway, that is irrelevant. So direction field, what did you get from direction field? You can exactly what you can do that without actually solving a given differential equation, you can have an idea about the solution curve. So here also, integral curves also, I mean, they are nothing but solution curve. So how you can do that with the help of giving differential equation? Let me tell you another trick. So what you can do, say, suppose, I mean, this is the point, suppose this is the point, x naught, y naught, okay? So you already know the value of x naught and y naught from the given initial condition. So then, obviously, then this is going to give you the value of the gradient of the curve at this point. So this is going to be simply given by f of x naught y naught. Okay. So once you have this slope, what we can do? We can simply draw a vector. Say, suppose this is the vector. Okay. And then what I'm going to do along the vector, I'm going to consider a neighboring point, say this one, and I'm going to call this point as x1, y1. And you already know the coordinates of this point x1, y1. And then again, what we are going to do, we are going to find out the slope at the point x1, y1 from the given expression here f of x comma y. So then successively you just go on doing this. So then it is going to lead you to some neighboring point of x1, y1, x2, y2, and then you go on repeating the process. Is it okay? Fine. So in that way, you can draw the integral curve. You can draw the integral curve. This I have taken from Simon's book. Okay, fine. So now, next, what we are going to do, we are going to go to the concept of uniform. Sorry, before going to uniform convergence, let me again do some stuff which yesterday I think I forgot to tell you. I told you only one part. Okay, right? So I can erase the board, right?
Yes, sir.
Yes. And again,
Yes,
let me
sir.
tell you. Yeah. And again, thank you. And again, let me tell you one thing. Like, you please, I mean, don't attend my classes just by, I mean, observing me telling you something. Please come with pen and paper. Okay. So, like say, that is really going to help you. It is not like simply attending, like say, sitting in front of your computer or your mobile phones. It is not like that. Please come with pen and paper. Okay, fine. So, what I'm going to do now, I will go back. I will go back to that Picard's approximation. I'm going to do a little bit about that, and after that, I'm going to do uniform convergence. Okay. See, yesterday, what I did, like I told you that I can have an integral equation. I can have an integral equation of this form. Okay, and I told you that 1 and 2 are equivalent. So basically, if say yx is a solution of this integral equation, then this is a solution of the given differential equation as well. Okay, so I did only one part. I probably what I did, like I integrated this given equation given by 1 between the points, I mean x naught and x, and then I found out that from there you simply get these expressions. Is it okay? So that is only one part. Okay, so this has to be satisfied both ways, if and only if. So basically, if this is a continuous, if say suppose something like this, y equal to 5x is a continuous solution of 2, then y equal to 5x will be a continuous solution of 1 also, and vice versa. Just the only if part I just want to do, and that is pretty straightforward. See, now if you differentiate 2, what you are going to get? If you differentiate 2, you are simply going to get y prime x. This is equal to f of what?
X comma y.
Simply x comma y. Fine. And again, if you plug in here, if you plug in 2 y x naught, then what is going to happen? In this integral, it is lower limit and upper limit. Both of them are going to be x naught. So basically, this is going to become 0. Is it okay? So y x naught is going to be y naught. So basically, what happens here? Like say, you can retain one expression from the other. You can retain 1 from 2 and 2 from 1. Okay, so that is why they are equivalent. So yesterday, I think I forgot to tell you this part. Okay, and again, it is quite funny that in many books, like say today, I was going through a little bit of Codrington's book on ordinary differential equations, and again the book on theory of ordinary differential equations. And over there, you will find a lot of lemmas, all this stuff. And let me assure you that you don't need to worry about this. So what they have done, like say whatever I have told you, this equivalence of these two relations. So over there, they have also described this as a theorem. Okay, I guess we don't need all this stuff. You have to understand this stuff. That's okay. Fine. So this is what it is. So I think yesterday I missed the bottom right part, although I told you about it. Okay, so now everything is precise here. Okay, fine. So now let me again do one more exercise from Picard's method of, successive approximation. And again, let me come back to that. So, and from now onwards, what I am going to do, I am going to simply refer to the initial value problem, like say dy dx equal to f of xy, subject to the condition y at x naught equal to y naught. I'm simply going to call it as simply 1. Even if I don't write it down, you should infer that it is simply that initial value problem. Okay, fine. So now, what happened in the Picard's method of successive approximations? We generated a sequence of functions given by this y1x, this is equal to y naught, x naught x, f t, y naught t dt, then y2x equal to y naught. Just you may be thinking that this is kind of boring, but I want this to become permanent in your brains. Okay, so y naught, then x naught x f t y n minus 1 t dt, and so on and so on. Okay, fine. So this is what Picard's method is going to do, successive approximation. Okay, so now let me try to so there is some notes on Picard, you don't need to worry about it. So I would like to do one exercise, so maybe exercise number 2. Exercise 2. So what it is, you have to find out the exact solution of the initial value problem given by y prime equal to 2x 1 plus y, and the initial condition is given to be y is equal to 0. Okay, and of course they are saying that you have to start with y naught x equal to 0. Okay. Now let me tell you one thing. Whenever you perceive the initial condition as this and the initial guess as this, you know they are different. The initial condition is simply nothing but a point. Is it okay? But the initial guess here, see what is happening here. The way I have written down this the sequence of function. So what is happening here? Here I am talking about a sequence of functions like this. Is it okay? This is infinity. Okay, fine. And this one is the very first function in this sequence of functions. So basically, this is going to represent a curve. In this case, this is a straight line. Is it okay with everybody?
Yes.
Right?
Yes, sir.
Yes, sir.
Yeah. At the top right, that was the initial condition, which was nothing but a point. But here, when we consider the sequence of functions, this is a straight line. This is a horizontal line. Fine. That difference you should remember. Okay, it is not like say simply you shouldn't think that this and these are the same thing. No, it is not the same thing. Okay, fine. So now if y not x equal to 0, so then what is going to happen? And here, of course, your f of xy, this is given by 2x into 1 plus y. Okay, fine. So now your y1x, this is going to be y0. Of course, because y0 is 0, so this is going to be 0 throughout. 0 throughout. I'm not going to write it down. Let me simply concentrate on this. So 2x into 1 plus y. So this is going to be, let me write it down first. So this is going to be f t y0 t dt. Okay. So this is going to give me x naught x. So f t and y naught t, this is simply equal to 0. So dt. So now if I use this formula, so and of course here also see x naught also I am going to replace it by, because the initial condition is given by this y at 0. So this is simply going to be 0 here. Okay, this is 0. This is 0. So this is 2x in place of x, 2t, then 1 plus y, t. This is y naught t, that is 0 dt. So basically, this is going to give you what? Eventually,
X squared.
x squared. And again, let me. What I have been observing these days that all the girls here, they are silent. You should also be vocal, right? The girls, I mean, you shouldn't let only the boys to speak up. Okay, sometimes you should also unmute and say yes. Okay, this is x squared. Fine. So then let me do it quick. y2x. So 0 to x, and then this is simply 2t. And then 1 plus, this will be replaced by y1t, isn't it? So y1t is nothing but t squared. Is it okay? So this dt, so it is, let me just for your perusal, I'm intentionally doing it because later on it may give you some trouble. Okay, so
This is 2t cube.
2t cube, yes. 2t cube. So this is going to give you x squared, fine, plus
X to the power 4 by 2.
x to the power 4 by 2. Fine, x to the power 4 by 2. I'll just work out a couple of more terms, and then I have some intention behind this. Okay, and then your y3x, this is going to be 0 to x, and again this is fixed 2t, then 1 plus y2t, and y2t is given by t squared plus t to the power 4 by 2. Okay, so dt. So this is 2t plus 2t cube plus t to the power 5, right? So eventually I am going to get what? Again, this is x squared, okay? This is x to the power 4 by 4, and this is
4 by 2. X to the power 4 by 2.
X to the power 4 by 2.
by 2, and this is x to the power 6 by
6.
6. Okay. So now a pattern is emerging. So from here, and this is from here, I have got an idea that I can simply write it as x squared and this as fine. Okay. So eventually you are going to get y and x. This is equal to x squared plus x squared whole square by factorial 2, and this is going to be x squared whole to the power n factorial n. Okay, fine. So now if I extend this series to infinity, like as now you can see, if I want to find out that what happens to limit n tends to infinity y and x, what is it going to give me? It is simply going to give me what?
E to the power x
E to
square
the power
minus 1.
E power
Minus
x square minus 1.
Yes. Yes. Okay. Who is this? I heard some voice, female voice. Can you identify yourself? May I have your name, please? But anyway, I am happy that some girl has participated. That's it. Okay, fine. So if you had 1 added here, it would have an e to the power x squared. So this is e to the power x squared minus 1. Okay, fine. So now, I mean, had you solved this differential equation, where are you going to get that? Let me just try to do it quickly. Okay. What is going to happen? So this is going to be dy by 1 plus y. So this is going to be equal to 2x dx, right? So this is going to give you, I mean, ln 1 plus y. This is equal to your what? Okay, let me write it down here. C e to the power x squared, right? Fine. And then when your x is 0, y is 0. So c is equal to 1. Is it okay? Fine. So basically from here you are going to get using y0 equal to 0 implies c equal to 1. So from here you are going to get y equal to e to the power x squared minus 1. Okay. So see, I'm not saying that you are always going to get this. Till now, I cannot say because I still haven't proved. I mean, this uniqueness theorem, uniqueness and existence theorem. I still haven't proved. But probably I have been able to convince you that if you can generate a sequence of functions like this by this through the method of Picard. So this sequence, at least in this particular example, it was seen to converge to the solution of the given differential equation. Is it okay? Fine?
Yes, sir.
Right? So that tells you that we are moving in the right direction. You may be thinking, why I have to rope in all this stuff? Why this method of successive approximation? So this has given us an idea that this method is probably going to work. That is where we are going to bank up later on. Okay. So this is about the. I mean, yes.
Sir, I think you have to give some range of x. Otherwise, this sequence will not converge to e to the power x square minus 1.
Can you tell me what will be that?
Means x must belongs to the open interval minus 1 comma 1.
Okay, you probably yes, yeah. Carry on. I'm listening.
So we need some restriction. Otherwise, this sequence will not, this series will not converge.
Okay, good. Okay, fine. See, now one thing is very important here. Whenever we talk about an initial problem, I mean, yesterday also I told you guys the same thing. We are seeking a solution in the neighborhood of that initial point, x naught, y naught. Okay? So that is what it gives you an idea that, okay, I should try to find a series which is going to converge in the neighborhood of x naught. Is it okay? Fine. So that gives you an idea that probably, I'm still not saying, I'm confidently, probably the interval on which the given series is going to converge, it is going to hover around, in this particular case, the point 0. Is it okay?
Okay.
Fine. So see, that is the hint. That is the hint. Whenever you are seeking an interval, right, you always try to find out an interval around that point. Okay, fine. And in most cases, it is going to work. I'm telling you. Until and unless, I mean, there is something wrong. Basically, until and unless it violates the conditions for the conditions for the existence and uniqueness. And yes, that you have reminded me. Let me tell you one more thing. Okay. Now, just give me one thing. Say this particular example, y0 equal to 1. Let me just try to give you a scenario. Okay, this is x, this is y. So now, obviously, at least this is my initial point. Say this is 1. This is my initial point. Okay. So again, this has given you an idea that the function is going to be monotonically increasing. So my graph, I mean, even if it starts from here, start from somewhere, say negative infinity to positive infinity here. So like probably it is going to be something like this. It is going to be something like this. Is it okay? Fine. Yes.
Yes.
Okay, yes, sir. Yes, sir. Okay. Now, think about this. When y is very large, right? From this formula, what is going to happen? We are going to get a very big gradient. Okay. So you know that if the gradient tends to infinity, you are going to get a vertical line.
Yes.
Right? Right?
Yes. Yes, sir.
So that means what is going to happen? In this particular situation? I am going to have a solution which is almost going to be something like this. And that possibility, probably it is going to violate those, continuity condition, differentiability condition. Are you getting my point?
Yes, sir.
Right? See what is happening here. So now, if you are trying to find, the derivative of the given function, in the neighborhood of the point 0, then what you are going to get? It is almost discontinuous there, isn't it?
Yeah.
Because for some x plus epsilon, here x minus epsilon, in both the cases here, y tends to negative infinity, here y tends to positive infinity, then what is going to happen? At this particular point, the value of y is 0, but here it is going to give you some abrupt jump, isn't it?
Yes.
Right? So you won't be able to find out the derivative there. Okay. So anyway, the analytical solution also, I am giving you the same conclusion that y equal to 1 is the only solution. So I can give another explanation like this. Okay, fine. So now I will come to, yes.
Could you please explain about the jump you told just now?
Okay, maybe I'll just explain it in one direction. Okay, fine. Say, suppose this is 1. This is y equal to 1. So now I have been giving that dy dx equal to your, this will be y minus 1 if y is greater than 1. Okay. Now when y tends to infinity, y tends to infinity, I don't know what is the value of x. Okay. So suppose I have taken a very neighboring point here. I mean neighboring point of 0. Neighboring point of x equal to 0. X equal to 0 plus here somewhere. So then what is going to happen? If y tends to infinity in the neighborhood of x equal to 0 itself, I am going to get some value of this slope, right, which is almost tending to infinity.
Yes.
Right? If it tends to infinity, you almost get a vertical line, isn't it?
Yes, sir.
Right? You basically you get a curve where the tangent is going to be vertical. Right? So that means I am getting 2 points. Where at one point the value of y is 1, and in the very next neighboring point it is abruptly increasing.
Okay. Got it.
Fine. So that is why the derivative there, the existence of the derivative is in question. Okay. So in that way also we can tackle this problem. That okay, it is going to have y equal to 1 as the only source. That's what I mean by it. Okay. Fine. Okay, I think the next thing on the agenda is uniform convergence. Okay. So, fine. I think you have done it enough. So now I'm going to come to uniform convergence, and this is very, very important. Like say, here we are not talking about only convergence. We are going to talk about uniform convergence and why that is mandatory in order to prove the existence and uniqueness theorem. Okay, I'll tell you that. So now let me come to the definition. And of course here, I mean in the definition, if you look at the slide here, I mean the x belonging to E. See here E is nothing but I have taken the definition from Rudin's book. Yeah, I have taken the definition from Rudin's book, and here we are going to assume that E is nothing but a subset of the real number. That's it. Okay, E is nothing but a subset of the real number. So basically, we are talking about x being real. Okay, fine. So as you know, it is well defined. Like say, if you consider a sequence Fn of functions, then what we say? We say that Fn converges to F. We say that Fn converges to F if what within epsilon greater than 0, right? There exists a positive integer. These are just kind of memorizing. Capital N such that Fnx minus Fx less than epsilon for all greater than equal to n. Okay. Now this is simply convergence. Okay. And what is pointwise convergence? In fact, this is the definition of pointwise convergence. It says nothing about. It says nothing about the dependence of this big number n. And again, let me tell you, this n is. You may be thinking that it is extremely big. I'll show you an example that it doesn't have to be necessarily that big. Okay, fine. So generally what happens? This capital N, this big N, it depends upon both epsilon. Because say this epsilon we are going to choose, I mean, arbitrarily. Okay, I could choose any epsilon which is greater than 0, however small. Okay, fine. So definitely we are going to choose our epsilon, and then if this capital N also depends upon our choice of x, then we say that it is a pointwise. The convergence is pointwise. Okay, and when it is uniformly convergent, when this capital N, it doesn't depend on the choice of our x. So then we say that the convergence is uniform. So obviously, I mean, a uniformly convergent sequence will be always, I mean, pointwise convergence. But a pointwise convergence sequence is not. Okay. So you please go through the definition once. Okay. So basically, what we'll be able to do, we'll be able to find a single big N for uniform convergence. Okay. Whereas in pointwise convergence, they are going to be different. Is it okay? So let me take, I mean, probably you have already done this many a times. Let me take this example. Probably you have checked this before, right? Should I repeat it, or I can simply jump to the proof of uniqueness and existence theorem? Should I do it?
Yes, sir.
Okay, fine. So here, obviously, I mean, and again, this is being considered in the closed interval 0, 1. Okay. So now here you can see that fn0, this is equal to 0, right? Okay. So this implies limit n tending to infinity fn0 equal to 0. Fine. And again, your fn1, this is going to be equal to 1. So your limit n tending to infinity fn1 equal to 1. Okay. Now, if your x lies strictly between 0 and 1, then also you will see that, I mean, limit n tends to infinity fn x, this is going to be what? 1.
0.
0. This is going to be 0. Okay. So that means if I say that like limit n tends to infinity fn x, it converges to the function f of x, then this f of x, it is given by your 0 if your x lies in this interval. Okay, close of an interval, this is equal to 1 for x equal to 1. Fine. Okay. So that means what is happening here? Say, suppose now I want to graph the function f of x. Okay. I want to graph the function f of x in this particular case. So my graph will be this blue line, okay, pairing the point this and this solid point. Is it okay?
Yes, sir.
Yes, sir.
Like
Yes, sir.
just visualize the graph. Just visualize the graph. So what happens to the graph? Can you tell me about the property of this function f of x now?
Discontinuous.
It has a discontinuity at the
Discontinuous
point
at 1.
x equal
1.
to. Yeah, that is a big statement. That is a big fact. You have to remember. Okay. So now let me come to the definition part. Let me come to the definition part. That I mean f and x, mod of f and x minus fx less than epsilon whenever small n is greater than equal to capital N. Okay. Now let me concentrate on these two. Let me concentrate on these two. Okay. Here, whatever is the value of n, whatever is the value of n, what you are getting here, you are always getting the, I mean, same value, isn't it? Basically, I mean, in the first case, simply the sequence is 0, 0, 0, 0, and in the second case, it is nothing but the sequence. Here, if I consider this sequence, your this fn0, if you want to write down, it is going to be simply this, isn't it? Fine. So similarly, your fn1, this is going to be simply this. Okay. So now what is happening? What is happening? See, in the first case, in the first case, the limit is 0. So that means fn1 minus 0, say suppose less than epsilon. Okay, epsilon can be any positive number. Less than epsilon. For all, I can simply say, can I tell this? Can I say this?
Yes, sir.
Sir, if n1 tends to 1.
Yeah, pardon?
Sir,
Yeah.
fn1 minus
Sir,
1.
limit. If n1 tends to 1 as n tends to infinity.
Yes, sir.
No, okay. What? Sorry. Yeah. Thank you. Okay, let me plug in 0. Fine. That is fine. Now I am fine. Okay.
Yes, sir.
Isn't it? So similarly, I am getting the same scenario. I am getting the same scenario for this, isn't it? So in both the cases, I can consider capital N to be simply equal to 1, isn't it? So this gives you an idea that this capital N doesn't necessarily have to be a very big number. Okay. So now let us come to the interesting situation. Like when x strictly lies between, when your x strictly lies between 0 and 1. Okay. Now here also, I'll have something like this. Okay. Now let me give you one example. So suppose I am considering x to be equal to half once, okay, and then x to be equal to say 1/10, right? So now your fnx in this case is this, and fnx in this case, this is. Okay. Now, what is going to happen? If you simply take, say, suppose I have chosen this capital N to be equal to say 100. I have taken this capital N to be equal to 100. So one effect this is going to have, that the same effect I will have from here if I maybe let me simply take it as 1 by 10. Okay, simply take it as 1 by 10. So it is going to be 1 by 10 to the power 100, right? And 1 by 10 to the power 100, you can get it from simply 1 by 10. Sorry, just a minute. Let me make it 1 by 10. Let me make it 1 by 100. Okay, so then simply by plugging in small n equal to 10, simply by plugging in n equal to 10, you get the same effect. Is it okay now?
Yes, sir.
Yes. See, firstly, I have taken x equal to 1 by 10. In the second case, I am taking x equal to 1 by 100. So now, see, I am trying to make both of them tending to 0. Okay, 1 by 10 to the power n and 1 by 100 to the power n. I am trying to make them tend to 0 by making small n as large as possible. Okay, what I want to say is that, say, suppose for this one, for this, I am trying to find out, say, capital small n greater than or equal to n1 for this series, and small n greater than or equal to n2 for this series. Okay, now this is going to give you an idea that definitely you have to choose capital N1 much larger than capital N2. Am I right?
Yes, sir.
Because
Yes,
this
sir.
second series is going to converge faster
Yes, sir.
towards 0 than the first
Yes,
series.
sir.
Is it clear now?
Yes,
Isn't
sir.
it?
Yes,
So
sir.
what is going to happen? Even without going to, like, you in my second example, I will do that methodology. So whatever methodology I am going to follow in my second example. In the first example also I could have followed it. Like, say, I would like to find out, I mean, capital N. Then probably you have already done it before. Then you will see that capital N is going to depend both on x and epsilon. But now this is good enough. This is good enough, isn't it? This is good enough because when your like, say, this denominator is large, you have to choose a smaller capital N. Then when you have to choose it for a smaller denominator. Okay, so basically what I want to tell you is that for all x lying in that interval, that capital N is going to be different. Is it okay? Fine.
Yes, sir.
Yes, sir.
Fine.
Yes,
But again, you can come to one conclusion. See, the same N also could be chosen. You can choose it to be the largest one. Okay, and that is going to work for all of them. You can think in that way also. But my point is that you have the choice. You have the choice of choosing different N. Okay, here. Fine. So this can give you one explanation, or otherwise what you can simply, I can think about this. From here, you can simply think about, because say x is definitely a positive number. So here this one, I can simply write it as, so from here, what is going to happen if I take log? So is it going to be less than or greater than? It is going to be less than. Okay, and this one, can you see? I mean, this is visible, or I should go up?
No, sir.
This is not visible.
No, sir.
No,
Not
Okay,
sir.
visible.
I'll go up. Okay, sorry. Okay, say I have got x to the power n less than epsilon. So this implies, okay, can I write it like this?
Yes, sir.
Why?
Because ln x is negative for x belongs to open 0, 1.
Exactly. See, that is smaller than, I am taking a fraction which is smaller than 1. Okay, fine. So that is why ln x is going to be negative, because we are dividing by a negative number. So there is going to be reversal in the inequality sign. Is it okay with everybody? Fine. So that means if we choose capital N to be this quantity, I mean this expression, then I mean this is going to be true, right? For all x and epsilon. Okay, but here you can see that this capital N obviously, oh, this is x. Capital N depends upon both epsilon and x. Okay, so now let us try to find out one example where, this sequence given by fn x equal to x to the power n, it is not uniformly convergent, but it is pointwise convergent. Okay, fine. So in the second example, in fact, second example you can easily prove. Huh? Second example, I'm giving you an
Sir,
yeah.
sir,
Yes.
in this example, if we change the domain, then it will also uniformly convergent. If we change the domain.
Yes. Strictly, yes. But which domain you want to change? Yeah, is it going to
Sir,
be?
if we take one end is 0 and other end is 1 by n, for in, so say 1 by half, just half, 0 half.
0 half. So, but it is similar to whatever I have explained, right?
Yes, sir.
No, it is not going to be. Sorry. It is because at least one point I have kind of discontinuity there.
Sir, the problem is, sir, here the problem is when x tends to 1, then ln x goes to 1 by ln x goes to infinity. This is the problem, because here n is equal to ln epsilon by ln x.
See, basically, let me tell you, let me give you a hint. Whenever you are going to get some discontinuity in that limit function, okay, you cannot get uniform convergence. Hopefully I am right. I still have to look at the books, but I think there is a theorem something like that. Okay, you cannot get it. Now let us take the second example. So I'll just give you a hint. In the second example, again the interval is that open interval. So second, obviously, I mean, if you consider the second example, x to the power n, obviously, I mean, what happens here? Like say this tends to 0 as n tends to infinity, isn't it, in that interval? Because x is always greater than 2. Fine? Okay. So then, I mean, this part, from this part, what you are going to get, x to the power n, and this is always less than, in this particular case, 1 by x to the power n, because x is greater than 2, because here there is no possibility of x being equal to 0. In that case, I will have equality sign. But since x is strictly greater than 2, I am going to have it. So from here, I mean, if you, again, this is going to be fine, because x is greater than 2. So 1 by x is, I mean, less than 1 by 2. So you are going to get this. And eventually, from here, if you plug this into the less than epsilon, from there, you are going to get the value of capital N, which is going to be independent of x. Okay? From there, you can prove the uniform continuity of this sequence. Is it okay? I think you can do it at home. Fine? You please do it at home. You prove that the second sequence is uniformly convergent. Okay, fine. I didn't get any answer, so you don't want to do anything at home?
Yes, sir.
Yes, you don't want to do anything at home, or no?
No, sir. No, sir. I will do, sir.
Yeah, just try it at home. Okay, fine. So
Okay.
now, let me again. Sorry. Just give me one word. 10 seconds. I'll just clean the eraser. Sorry. Now one thing I want to say. Why what is the significance of all this stuff? Like why I'm emphasizing so much on uniform convergence. Okay. Why uniform convergence? That's a time. So why uniform convergence? Okay, fine. As I have told you that while proving your uniqueness and existence theorem, we will try to generate the sequence. We'll try to generate a sequence. Fine. Of course, generate a convergent sequence, which assuming that it is going to converge to some function yx. So this yx is going to be the solution of the given initial problem dy dx equal to f of xy and yx naught equal to y naught. So that is what our intention is. Okay. Now let me come to the point why I am seeking uniform convergence. Okay. Now, for example, suppose I have generated a sequence like the previous one, the very first example, say x to the power n. Okay, and I have got, like, say f of x, and let me call that as y of x as the limit of this sequence. Okay, and now if I want to graph it, then what happens? My solution is this. My solution becomes this. Okay? My graph of the function, it is going to look like this. The graph of the function yx, right? Which is nothing but the limit of this sequence, it is going to look like this. So far, so good, right? At least up to this, I think you have understood what this is basically mechanical. Okay, fine. So now, say suppose I am seeking the solution of this initial problem in the closed interval 0. Okay, if it has the solution y of x, definitely this being a first order differential equation, I would require the existence of derivative at all the points. Is it okay? In that interval, existence of at least first order derivative, right? Now, because of the discontinuity of the limit function at this point, I cannot get that condition. I cannot get the differentiability condition there. Is it okay? Fine. Now, probably you have understood why the uniform convergence is essential. Is it okay?
Sir, can you repeat this one? I
See,
have some internet.
Or you have some internet issue. See, now what we will try to do while proving the uniqueness and existence theorem, we will try to generate a sequence like y and x. Okay, and what we will do, like this sequence is going to converge to some function y of x, and that function we are going to claim as the solution of the given differential equation. Okay, fine. So now the question is why I am seeking uniform convergence, not pointwise convergence. It is because, say, suppose if I have a situation like before, like the very first example that I have taken, like say suppose my sequence was something like x to the power n, which eventually converts to a function whose graph would look like this, whose graph would look like this. Okay, fine. So this is nothing but the graph of y equal to x. This is nothing but the graph of yx. Okay, it has a discontinuity at the point 1, right? But if I have to consider this yx to be the solution of this rescheduled problem, I need first order derivative of the solution existing at all the points in the interval of definition, which in this case, if it is the closed interval 0, 1, then I don't have the existence of the first order derivative at the point 1. Fine?
Yes.
So now probably you have understood why that uniform convergence is essential. Only uniform convergence can give you a continuous curve in the given interval. Okay? So now it will be clear to you. So this is final theorem. Uniform convergence of a series. I'll discuss about it. Don't worry about it. But what I have told you, that brings me to the last theorem. See, if Fn is a sequence of continuous function on E and Fn tends to F, okay, uniformly on E, then F is continuous on E. It is always going to guarantee me a continuous limit, and if we consider that limit to be the solution of the given differential equation, we are fine with that. Now, is it clear?
Yes.
Yes?
Sir,
Yeah.
up
Yeah.
to continuity we can say, but how can we say differentiability?
Up to, can you repeat your question? Up to
Continuity of the limit, it's okay, but how can say about differentiability?
if the function is not continuous, how can you differentiate it?
No. Here, suppose ynx converges to yx uniformly.
Okay,
Then
yes.
yx continuous.
No, I'm not saying yx is continuous. No, I'm not saying yx is continuous. If it is uniformly, yes. If it is, uniformly convergent, then yx is going to be continuous. Yes. Yes.
But we can't say anything about differentiability.
Of course, if there is a kink there, of course, it is going to depend upon the function. It is going to depend upon the function. But continuity is, a prerequisite for differentiability, isn't it?
So that limit may be a solution of the differential equation, but we can't guarantee now.
That is what it is. But if it is not continuous, we cannot get a solution at all. At least it has given me a possibility, right?
Yes, sir.
At least it has given me a possibility, right?
Yes, sir. Yes.
But if that possibility is not there, I cannot think about the existence of this differential equation at all. But
Yes.
I am going to prove that this limit is going to be, differentiable. Okay. Basically, see, okay, I'll answer to your question. See, now we have already proved the equivalence of equation 1 and equation 2. Equation 2 was that integral equation. Okay, fine?
Yes.
Okay, and all the terms in the sequence generated by Picard's approximation, they follow equation 2, something like equation 2. Is it okay?
Yes, sir.
Fine. Since equation 2 and equation 1 are equivalent, that is going to guarantee you the differentiability of that limit function. Okay, we will do that, don't worry. We are going to do each and everything we are going to do there. Okay, fine. And again, this uniform convergence of a series, you already know how to prove the convergence of a series. So what we are going to do, we are going to generate a sequence of nth partial sums And if we can prove that the sequence of nth partial sum is convergent, then the given original infinite series is also going to be convergent. Okay, that is what we know. Okay, so that will bring me to, I don't know whether I'm going to start it today or not, but just have a look at this. So on Saturday's class, I don't think I'm going to use any slides. So I'm going to do only blackboard teaching. So hopefully, I mean, just Tanai has a complaint. Not really complaint. His complaint is my complaint also. Okay. I mean, his complaint is to me, but my complaint is to Microsoft. So they don't allow to record this in such a way that my blackboard teaching becomes the bigger panel. Okay, it always keeps the slide as the bigger panel in the recording. So that is the problem. So if I don't use slides at all, hopefully on Saturday's class, so then you will get to see only the whole blackboard in the recording as well. Okay. So now look at the existence and uniqueness theorem here. So probably you have gone through it umpteenth number of times. But here, what they have done, although they are talking about a rectangle R, but eventually they are going to seek the uniqueness of the solution only in the neighborhood of that initial point x naught. You please go through the theorem here once, and probably I'll stop that. I'll stop that. Stop it here, because again I'll have to restart from what I left in my last class. So I'll stop it here. Okay. Do you have any question? I may take some questions from you. So maybe what I can do, I can just a minute. How can I get rid of this? Just I'm just trying to unshare it. I'm not getting the question. Okay. Anyway, I mean, if you have any questions, just ask me. I'm listening. Meanwhile, I'm trying to. Yeah. Do you have any questions regarding this course? It doesn't necessarily have to be from the course content. Yes. Do you have any question? I mean, no. So okay then. If you don't have any questions, so then I'm going to meet you on Saturday. Okay. At 12. Okay. Fine.
Okay,
Thanks.
thank you.
Yes, sir.
Okay.